Yeah. So welcome to week 10 of the NPTEL MA106 Category Theory course. I am Shubhajit Dash. I am a PhD student at the Department of Mathematics at IISc, and as we keep doing every week, we'll be solving problems based on the content of this week. But first, we'll have a small review of whatever was covered during this week. So thanks to Pranay, I have all the details of all the lectures. So uh, I'll quickly go through whatever was covered this week. Okay, so in this week, by the way, I hope I am audible, right? Okay, thank you. So in this week, so these are the things that you learned. So what comes first? Okay, so you saw the very important. So as I was mentioning last week, we had just started working with abelian categories, and as I mentioned, that abelian categories are like the gateway towards categorical algebra, which is a pretty huge area, pretty vast area. And one of the things which I'm sure people who have studied algebra have already seen previously, at least in the case of modules or maybe groups, is the notion of an exact sequence, which actually now makes sense in more abstract context, more precisely in the context of an abelian category. So you saw the very important notion of an exact sequence. In an abelian category. Okay. So what is it exactly? What is exactly an exact sequence? So you take, so let A be an abelian category. A sequence, by which I mean a path of arrows, a path of composable arrows, a sequence of objects and arrows A, B, C. Let's keep three objects for the time being. F, G is said to be exact if, when do we call it exact? Yes. Yeah. So if image of F, and since we are doing category theory, I mean it's perfectly okay if we say image of F is equal to kernel of G. That perfectly makes sense because both are sub-objects of B, and we can talk about equality of sub-objects of an object in a category precisely because we know that sub-objects are exactly, equivalence classes of monomorphisms going into the object B. So it makes perfect sense to say when two equivalence classes are equal. But sometimes people do relax this condition and instead just ask for an isomorphism from im F to kernel of G. But I would advise, if you are working with this notion, it's better to always maybe consider equality because there's no harm in doing that. But again, category theory, so isomorphism, strict equality is something which is too strict for us. Okay, so if image of F is the same as the kernel of G, so what was the definition of the image of a map F in a category, in an abelian category? What was the definition of image of f in an abelian category? So image of f is equal to the kernel of the co-kernel of f, and we know what the kernel of G means. So this should be isomorphic to the kernel of G. So this in particular, observe that this in particular actually implies that G composed with f is equal to the zero map from A to C. So note that. This implies that G composed f is the zero map from A to C. Okay. So this is the notion of an exact sequence. Again, there are other alternate ways of phrasing the definition, but this is the one which is the most popular. Okay. Now I'll call a sequence, a general sequence, a sequence of objects and arrows. Okay, let's say is said to be exact at B if this happens, and a sequence of objects and arrows in A of this form. So you have an object, an arrow, an object, an arrow, an object, an arrow, and so on, is said to be exact if it is exact at every what should be the word for this? If it is exact at every internal, I don't really like the choice of the word, but okay. If it is exact at every internal object, let's say, where internal actually here means just, I mean, an object, so that it is the codomain of some arrow as well as the domain of some other arrow. Okay. And an exact sequence of this form of the form 0 A B C 0 is called a short exact sequence. And there are of course, I'm sure all of you have seen what this means in more detail. So this implies certain, or this is rather equivalent to certain conditions on the maps on the map from A to B, the map from B to C. So we won't repeat all that. Okay, so what else? So you also studied the very important notion of an exact functor. So what is an exact functor? A functor f from a abelian category A to an abelian category B of abelian categories. Let's write it like this. Is called exact if it's called exact if exactly if preserves exactness of sequences or exact sequences. So we saw what the notion of an exact functor is. We also, I'm pretty sure we also saw the notion of a left exact functor and a right exact functor, right? I mean, the names are pretty clear what that should be, right? So let's just write down the names. We saw left exact functors, and right exact functors. So left exact functors are exactly those which preserve kernels, and right exact functors are exactly those which preserve co-kernels. Equivalently, left exact functors are those which preserve uh, if you take a short exact sequence of this from 0 to A to B to C, let's say, there's no 0 at the other end. You can also ask for one, doesn't really matter, but the point is that if this sequence is exact, then its image will also be exact. So 0 to FA to FB to FC, that's all that you have. You can't go to, you can't talk about 0 at the other end. This is what a left exact functor is, and dually you have the notion of a right exact functor. Simplest way to state their definitions are left exact functors are exactly those which preserve kernels, and right exact functors are exactly those which preserve co-kernels. And as it turns out that this simple definition or this simple requirement is rather enough to actually show that left exact functors are additive. So in particular, this means that they preserve byproducts. So that means they preserve finite products. So they preserve finite products and they preserve kernels, which are exactly equalizers, which means that therefore they preserve all finite limits. They are Cartesian functors. And similarly, dually right exact functors are co-Cartesian functors. They preserve all finite co-limits of all finite shapes. And sometimes, this word or this name is sometimes sort of even abstracted a bit more, in which case people might not have abelian categories in the picture, but still one can talk about functors which preserve finite limits. We already have a name for those, Cartesian functors, but they are also sometimes called left exact functors in general context. This is the reason for calling it so. Okay. So what else? Okay. So one of my favorite things is perhaps what we are going to rather recall in short is the notion of a Grothendieck category, which is like it's a superb, it's an absolutely beautiful notion of a category. And the purpose was to encapsulate properties of module categories, categories of modules over rings, in particular the category of abelian groups. Okay. So we know what an abelian category is, but just for the sake of completeness, we just quickly recall. So within the categories, yeah. So we recall first that an abelian category is a pre-additive category. Is it okay now? Okay. Is a pre-additive category such that firstly, so we recall that an abelian category A is such that we recall that an abelian category A is a pre-additive category such that A has a zero object, A has binary products, and hence we can say binary coproducts, because we saw that an additive category is exactly a ringoid in which there is a zero object and there are binary products, and this is enough to actually show that binary coproducts also exist and they are isomorphic to binary products. Oops, what just happened? Yeah, I'm sorry about my connection today. join. Just a second, I'll try changing my connection. You can see my screen, right? Sorry for the interruption. Thank you. So yeah, A has binary products. It has a zero object, and hence it has binary co-products. So binary, yeah, as I was saying, in an additive category, we already know this, that having a zero object and having binary products is enough to show that binary co-products exist and are isomorphic to binary products, which we actually call biproducts. A has kernels and co-kernels. And monomorphisms are regular, and epimorphisms are regular. So monomorphisms are equalizers of some parallel pair, and epimorphisms are co-equalizers of parallel pairs. So so that means that monomorphisms are kernels of something, of some arrow, and epimorphisms are co-kernels of some morphism. So this is what an abelian category is. But it turned out that to capture more nicer and stronger examples, and in particular to actually do module theory in more abstract contexts rather than just sticking to modules over rings, what one needed, or rather what Grothendieck needed, was some further axioms which sort of got encapsulated into the definition of what is now called Grothendieck categories. So I'll just mention the axioms quickly. So first of all, observe that this definition actually implies, and we saw this last week as well, that abelian categories are finitely complete and finitely co-complete. That is, they are Cartesian and co-Cartesian. But we saw an example of an abelian category which is not actually complete. That is, does not have all small limits, or does not have all small co-limits. So we would like to sort of remedy this situation and instead ask or demand that our categories, our abelian category, should have that property as well, which is actually what is known as the AB3 axiom, which says that, okay, so for a Grothendieck category, one needs, in addition, So we have all the above axioms. We have an abelian category. In addition, one needs AB3 axiom, which says that A has small coproducts. And notice that if it has small coproducts, we already know it has co-kernels, so it has co-equalizers, which means that it is co-complete. So equivalently, one can say that A is co-complete, has all small co-limits of all small sets. This is our AB3 axiom. Then one has AB4 axiom, which says that coproducts are exact. What do I essentially mean by this is the following, that so what do I mean by this? Can you answer? Coproducts are exact. Would you like to answer this, or should I continue? Okay, so coproducts are exact means that, so suppose I is a set. So by this I mean that if I is a set, any arbitrary set, and for every I in I there is an exact sequence let's say a short exact sequence 0 to AI to BI to CI to 0. Let's say this is FI, let's say this is GI, right? Then we can also ask this question, what happens to this sequence? So then the sequence, so essentially what we are doing is just taking a coproduct of sequences, by which essentially means that we are taking a coproduct of individual terms, entries of the sequence. So then the sequence 0, coproduct of zeros is 0. So coproduct of copies of initial object is just the initial object. Coproduct I in I, AI, to coproduct I in I, BI, to coproduct I in I, CI, to 0 is also exact. And we can guess what these maps in between are. So this is coproduct FI, this is coproduct GI, I in I in I. Okay, so this is all that it says. Coproducts, yeah. No. That's a good question, and that is actually the last axiom that we want. You can ask this question, can you give an example where coproducts are exact but direct limits are not? I don't really know if there's an example, but since there's an AB5 axiom, so I'm pretty sure they are not the same. It doesn't imply. But, okay, we'll come to that. There's something interesting that we can say about this, but we'll come to that later. But yeah, so AB4 is coproducts are exact. We understand what it means right now. AB5 means direct limits, as Pranay said already, direct limits are exact. So what do we mean by this? We can frame the definition now. Yeah, and we should, so yes. And what do you mean by the co-limit of it? You mean that co-limit of individual entries, right? Yeah. So direct limits are exact, by which we mean that if, so we should, instead of having a discrete category which we had earlier, we now should have a directed set. If I is a directed set, we know what a directed set is. It's a set in which every pair of elements has an upper bound. It's a poset in which every pair of elements has an upper bound. If I is a directed set, and for every I in I, I in I, there is an exact sequence zero to AI to BI to CI to 0, GI, FI. Is this enough, by the way? No, right? Because we have taken a directed set, we should ask for something more. What should we ask for? Yes. I'm sorry, 1 second. Yes, I got your answer. Yeah, correct. Absolutely perfect. Yeah. So, and for every I less than j, there is an arrow. I'm sorry. There is an arrow. Yeah, for every I less than equal to j, there are arrows. Let's put it like this. There are arrows. So we have this sequence 0 AI BI CI 0 FI GI 0 AJ BJ CJ 0 GJ FJ. We should have an arrow here, we should have an arrow here, we should have an arrow here, making everything commute, making the diagram commute. So notice what we have in each individual entry. What we exactly have is we can of course take identity arrows here. So yeah, in each individual entry what we have is exactly a diagram of a diagram whose shape category is a directed set. So we can talk about the direct limit of this diagram, that is the co-limit of this diagram. So making the above diagram commute, there are arrows making the above diagram commute. Then we have this sequence is exact. I in I, AI, limit I in I, BI, limit I in I, CI, 0 is exact. And these maps are again clear. So let's just write them. Oh, I see. I think if we wait for some time, it will come. Yeah. So just to clarify, what are these maps exactly? So from limit AI to limit BI, what is this map limit FI? What exactly is this map limit FI? Or rather, how do you obtain this map? How do you obtain this map limit Fi? Sorry. So this is exactly obtained from the, sorry. Yeah, how do we obtain this map limit Fi? uh, we stick to this note. I'll just come in a minute. Yeah, can you tell me how exactly do you obtain this map limit fi? I'm audible, right? Okay. Yeah. So we obtain this map limit fi using the universal property of the co-limit limit ai, right? This is exactly that. Okay. Yeah. So I was asking how do we obtain this map limit fi, or what is this map limit fi? The limit of all the fi's. Yes. Yes. We need to use that. So think about this pictorially. You have one diagram of AIs, you have another diagram of BIs, and for every I you have a map from AI to BI. Now you can take the co-limit here, you can take the co-limit here, right? Using the map FI, what you can do is you can think of this diagram, or rather you can restrict this diagram. You can restrict this co-limit of the BIs to obtain a co-cone with the vertex. The vertex is limit bi, but it's a co-cone for the diagram ai of the ais. So what I'm saying is you can use the universal property of the co-limit of ais to obtain this map. So there should be a unique map making all the relevant triangles commute. That unique map is exactly limit fi, and similarly you obtain limit gi. So what we just ask in AB5 is that this direct limit of these exact sequences should be exact. Okay. So these are AB3, AB4, AB5. These are pretty strong axioms, and okay, I'll mention that point what I was going to say at the end, because we'll rather solve something which will be useful. So we can figure everything out by ourselves. So yeah, I'll quickly go through the rest of the stuff. Oh, by the way, a Grothendieck category is a co-complete abelian category which satisfies AB5 and has a generator. And sometimes people do instead equivalently say has a family of generators, but we know that if a category has co-products and it has a family of generators, then you can club them together into a single generator. So it's enough to say that it has a generator. Okay, so this is all about Grothendieck categories, and examples I'm pretty sure we have seen. The most important examples are categories of R modules. So R mod for a ring R, then even more important are sheaves on a we know what topological spaces are. So sheaves on a topological space, and something even more general, which probably we'll see in the I think the last lecture maybe. Sheaves on a Grothendieck site, etc., etc. Okay, so what else was done? So we also saw localization of categories. So I'll just quickly mention the ideas now, not mention the exact definitions, because you guys can I'm sure you have already seen the lectures, but you can still get back to the lectures. So localization of categories was covered, and what exactly does it do? It does the same thing as we have what we do in the case of localization of rings. Rings rings can be thought of as one object categories. They are precisely one object pre-additive categories, right? One single object ringoids. So what do we do in localization? We demand that certain elements should be made invertible. So we want to obtain some new ring in which certain specified elements should be invertible. The same thing happens in the case of categories as well. Categories have some algebraic structure which is composition of arrows, and under composition we asks that certain arrows should be invertible or should be made isomorphisms. So this is what, roughly speaking, the purpose of localization of categories is. There are various different ways of defining it, and it has a universal property. One can define it using a universal properties. So I'll just mention universal property. What was the approach taken in the lectures? Was it the universal property? Are you aware? Okay. So okay. Yes. 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 Okay. So it's exactly the same it's exactly parallel to how localization is done for rings. That's the universal property. And localizations also have an alternate description. Was it? So Gabriel-Popescu theorem was also covered. Okay, so that means the other approach was also given, which is so basically localization can be seen as a pair of adjoint functors actually, in which the right adjoint is fully faithful and the left adjoint is exact. So I'll just mention this for now. Localization of categories can be defined using universal property, mimicking that for rings. What else was there? So multiplicative systems, series subcategory, localization at a series subcategory, etc. are all non-examinable. But yeah, I would definitely mention that series subcategories are really powerful subcategories. They are exactly those which are closed under sub-objects, quotient objects, and extensions. There is one can phrase it entirely in terms of exact sequences by saying that if you have a short exact sequence in your big category, so a series subcategory is a full subcategory such that if you have a short exact sequence in your big category 0 to A to B to C to 0, then A and C, the objects A and C are in the subcategory if and only if the middle object B is in the subcategory. And an interesting example is let's say Noetherian modules, etc. Yeah. Or in fact, you can also just Noetherian. Yeah. Sorry, I was going to say finitely generated as well, but that doesn't work. Okay. What else was covered? Gabriel-Popescu theorem. I'll just mention what it does because I'm sure the statement was covered. What does it say? It says that if you take, so it essentially identifies grothending categories as localizations of module category, categories of modules over a ring. Over rings. So it says that if you have a Grothendieck category C, let's say, and if you let's say G is your generator, G is a chosen generator in your Grothendieck category, then you can consider the monoid of endomorphisms of G. It will actually be a ring because you already have pre-additive structure. So you take the ring of endomorphisms of your G. Let's call it, let's give it some name like R, let's say. And from A to R mod, you take this functor. What does it do? It sends every object X to hom G comma X, let's say. I mean, you just take the functor hom G comma gap, right? So this actually is a functor from A to R mod, and it turns out that this functor is fully faithful, which means that you can realize A as a subcategory of, as a full subcategory of R mod, and this functor actually has a left adjoint which is an exact functor. So this is an alternate way of describing localizations again. So usually when you have a category and if you have a fully faithful functor from this category to some other category, then we say that this first okay, I'll join back, but let me continue. We say that this first category is actually a subcategory of the original category. You can identify it as a subcategory. If it turns out that this fully faithful functor has a left adjoint, this is what exactly what we call a reflective subcategory. So I'll say that the subcategory is reflective, and I'll say that the left adjoint functor that we have is actually a reflector in this case. And if the left adjoint in addition is exact as well, then we can actually see, I mean, we know the definition of localizations, we can actually see our subcategory as a particular localization of our big category. So, and in fact, what was I saying? In fact, one can actually, what was I saying? Sorry. Reflective, and yeah, and we can actually realize, I mean, always we localize with respect to, as Pranay already mentioned, we always localize with respect to a class of morphisms or with respect to a localizing subcategory. So that localizing subcategory can be obtained by looking at the kernel of the left adjoint functor. So you essentially, roughly speaking, you essentially look at the subcategory of your big category, which gets mapped to the zero object of your smaller category of your, I mean, the localized subcategory, the category which we want to see as a localization. So it's called a Serre localization actually. But yeah, please go get back and do check the statement once. Don't trust everything I say, but yeah, I'm sure this is what the statement is, and this is what it does. Okay, so what else was there? Yeah, that is what I'm trying. By the way, in lecture 2 I see properties of Grothendieck categories, existence of injective cogenerator, etc. Was all this proven? Just mentioned. Okay. Let me see if the record, yeah. Yeah, so I'll just mention properties of Grothendieck categories. Interesting thing is Grothendieck categories do satisfy the hypothesis of SAFT, the special adjoint functor theorem, by which, I mean, if we recall this, so if F is a functor from a Grothendieck category A to a Grothendieck category B, both of which are locally small, and let's say F, this functor F, I mean, let's say your domain category A has is well powered. is well powered and has a co-generator and is complete and is complete, then your functor f has a left adjoint if and only if it preserves limits. And it turns out that Grothendieck categories do have this property because they actually are something called locally presentable categories, which we have seen previously. Something categories which can be approximated in terms of filtered co-limits or direct limits of a special class of objects, which are precisely or finitely presentable objects. So I'll just mention properties of Grothendieck categories. Very important, or rather very interesting as well. The Freud-Michel embedding theorem, which says that if you take any small abelian category, then you can actually realize it as a as a fully as a full subcategory. I mean, you can, okay, let's put it this way, you can embed it fully, faithfully and exactly into a category of modules over some specific ring. Was a proof of this done? Okay. So Freud-Michel embedding theorem was seen, and cohomology of chain complexes. Okay, and the dualizing is straightforward. So homology of chain complexes. Okay. So yeah, I think we have spent a lot of time. Let's quickly get back to solving problems now actually. So we'll solve problems one by one. I'll keep problem one, or rather we'll solve problem one later. We'll come to this. Let's start with something a bit more simpler. Yeah. So this is our question. What we are given is an abelian category C. Just an abelian category. We don't assume anything extra out of it. What we want to show is a monomorphism alpha in our abelian category from A to B is essential if and only for all morphisms beta from B to C. Beta alpha is a monomorphism, implies alpha is a monomorphism. So we'll break the statement down one by one. But before that, since I believe he has proven Freud-Michel embedding theorem, he has also talked about essential monomorphisms and injective hulls or envelopes. Okay, so we know what an essential monomorphism is. It is exactly a monomorphism whose image is an essential subobject. So what is an essential subobject of an object? It's a subobject of that object such that if you take any arbitrary subobject of your target object, then big object, then that subobject, if that subobject is non-zero, it will intersect. Okay, so let's write it. So image of alpha is an essential subobject means essentially that. So image alpha is an essential subobject of B means that for all subobjects, for all non-zero for all subobjects, B prime of B with B prime not equal to 0, B prime intersection image of alpha is also non-zero. And what do we mean by the intersection of two subobjects of an object? Yes, so we take B and we have B prime, we have image of alpha, we just found the pullback, which by the way exists because we are inside an abelian category which is finitely complete. So this pullback is actually what is referred to as our intersection. Okay, so this is what we know what an essential monomorph is. Yes, you have a question or a comment. Yes, so it's so B prime intersection image of alpha will be a subobject of image of alpha as well as a subobject of B prime, because monomorphisms in any arbitrary category are always stable under pullbacks. Okay, so let's write that as well. I mean, let's indicate that as well. Yeah. Okay, so what do we want here? Let's break down the problem. So C is an abelian category. We want to show that a monomorphism alpha from A to B is essential if and only if this monomorphism alpha has the following property, that for all morphisms beta from B to C, beta alpha is a monomorphism implies alpha is a monomorphism. So what is the property of alpha? Alpha's property is this, that for any morphism beta from B to C, whenever beta alpha is a mono, then alpha is also a mono. So let's write it in a less confusing way. So the following statement holds. The following statement holds. Sorry, yeah, the following statement holds. This is our statement, or this is our property that we. No.
Hello.
Sorry. This is our property that beta alpha. Okay, I'll just call you in. I'll just get back in 2 minutes. I'm sorry.
ओके ठीक है. और इधर इधर इतना बड़ा होटल है, लेकिन खाने का अरेंजमेंट ये 2-3 आइटम का कौन. ना हम लोगों को बोला क्या खाना लेंगे, तो मैं ना 2 आइटम बोला. ओ अच्छा ठीक. और बाकी जगह में तो कोई दिक्कत नहीं होगा. तो काल बताने से भी चला.
Yeah. So sorry for the interruption. Yeah. So getting back to the problem, if and only if the for all, yeah. What do we want to show? We want to show that a monomorphism alpha from A to B is essential if and only for all arrows beta from B to C. The following statement holds, that beta alpha is a mono should imply that alpha is a mono itself. Right. So let's try this one, and let's try one direction and then we'll get to the other. So let's try the forward implication. So we assume that alpha from A to B is essential. So assume that alpha from A to B is essential. What we want to show is regardless of any, if we take any arbitrary morphism beta from B to C, then beta alpha is a mono should imply alpha is a mono. Okay, so we take a morphism. So take is an essential mono. So take an arbitrary morphism beta from B to C such that beta alpha, which is a morphism from A to C, so beta alpha means beta composed alpha, is a mono. What we want to show here is alpha should be a, oh oops, I think I have made a mistake here. I think it should be it should be beta obviously, because alpha is already given to be, how do you show this? We want to show that, so we assume that alpha is an essential mono. We take an arbitrary morphism beta from B to C such that beta alpha is a mono. We want to show that beta is a mono. How do you show this? Any ideas? So A to B to C, alpha beta. We have assumed beta composed alpha is a mono. We are all, keep in mind we are already given that alpha is a mono. This is irrespective of the problem. We are given, this is irrespective of what we want to prove. This is given to us already. Alpha is a mono. We have assumed that this monomorphism is an essential monomorphism. So I can put this here. I can put a barbed tail here. And I have assumed beta composed alpha is a mono. I want to show that beta is a mono. How do we show this? Any ideas? Okay, we should take the kernel of beta and try to show that the kernel of beta is 0. Okay, so what do we do? Okay, so I'll write it in this way. Kernel is a subobject of B. Let's say this is kernel of beta. Unless kernel of beta is 0. So if kernel of beta is not non-zero, then image of alpha intersection kernel of beta is non-zero. Okay. What do we do next? Any ideas or any suggestions? What can we do next? So try to think about this. Kernels, so if we, for the time being, if we forget that we are in an abelian category and let's just focus on, let's say, the category of modules, or let's say the category of abelian groups, then if you take a homomorphism of abelian groups F, let's say, from A to B, what is exactly the kernel? The kernel is the fiber of the map over 0, right? Now question is, can we write the kernel? We know already that kernels are equalizers, but can we write them as pullbacks as well? I mean, there's a reason I'm asking this, because why do we want to bring pullbacks into the picture? Because the entire definition of essential monomorphisms is framed in terms of intersections, which are just pullbacks. So we want to make use of this fact that we have pullbacks. So what we want to do is phrase everything in terms of pullbacks. So what the question is yeah, okay, okay. No, so but this is what I'm asking. What I mean, we want to obtain kernel of beta as a pullback, right? So we don't have kernel of beta a priori. Can we write kernel of beta as a pullback? I mean, sure we can, because we know that equalizers and binary products suffice to give you. Pullbacks and terminal objects give you all finite limits of all limits whose shape categories are all finite. So we can certainly write kernels. There is a morphism 0 from B to C. Okay. Yeah. So the kernel is the equalizer of this. Oh, okay. Okay, I get your point. So let's write it this way. So B to C we have 0. B to C we have beta. We take the pullback here. So what we have is something. Together with this, we take this pullback squared, and let's say this is beta prime. This will be a mono because this is a mono. So P is a sub-object of P, and in fact P will exactly be the pullback of I mean, one second, it should work, right? Because we take x, y, beta x is equal to 0. Yeah, this will work. I mean, there's an issue with this. This won't actually help us. But yeah, can we simplify this even a bit further? I mean, do we really need a B here? We just want a 0 map, right? That's all that we want. And in fact, just to simplify everything, we can just take 0 object itself, right? So this now looks perfect. So beta 0, beta prime, and this P will actually be. So I'll just say check that kernel of beta, right? This is our inclusion. I'll write an inclusion here. So kernel of beta will be a sub-object of P, right? And let's say 0 to C we have 0 map, right? No need to name this beta prime. There is always a unique arrow. So check that kernel of beta together with its inclusion into B fits into this pullback square. Okay, now how do we use this fact? How can we make use of this fact? what we want is image of alpha intersection kernel of beta should be non-zero, right? So how do we make use of this fact? And in fact, it would be better if we work in what should I say, in the not in the negative sense, right? So maybe we should assume that, I mean, we can just work with the contrapositive and rather try to show that something is zero. So we assume that let image of alpha intersection kernel of beta is equal to 0. What we want really here is to show that kernel of beta has to be 0. That is what we want. That would finally conclude that beta is a mono. Right. So, and again showing something is 0 is easier than showing that something is non-zero. It's the same thing, but just working with the contrapositive would probably be better. So we check that this fits into this pullback square. Now let's see an amazing thing about pullback squares. So B to C, let's try to fit everything properly. 0 to C0, this is kernel of beta, this is our inclusion, right? This is a pullback square, and from A to B alpha, what are we prompted to do right now, or rather provoked to do? We take another pullback. So what is this pullback? So A to B alpha, kernel of beta to B, this, let's call this pullback P. We take this pullback. What is the interesting thing about pullbacks that we know? Which that we know, and you mean pullbacks, right? Not just commuting. If two boxes are pullbacks, then the circumference box, the outer rectangle, will be a pullback. So that means P will actually be the pullback of this map and the 0 map. What is that actually? That is exactly the kernel of beta composed alpha, right? Exactly the kernel of beta composed alpha. So this is the kernel of, so P is actually isomorphic to kernel of beta composed alpha. I'll just put this in brackets as pullback squares are closed under gluing. Okay, so we have kernel of beta composed alpha is this, and what do we know about beta composed alpha? Beta composed alpha is a mono, so kernel of beta composed alpha is 0. This we know is 0. Moreover, what is P? P is also this pullback. We haven't really used the fact that P is the, I mean, let's write it nicely. P is actually the pullback of this diagram. We haven't used that fact. So what is this P actually? Can we say something nice about P? Alpha is a mono. We have to keep this in mind. It was already given to us that alpha is a mono. Yes, I mean not a property. Can we say something nice about P? Can we write, point out that this is exactly P? So we have kernel of beta to B inclusion, and alpha is a mono, so A can also be thought of as a sub-object of P. So what is this pullback? This is a pullback of two sub-objects essentially. What do we know about it? We have already seen it, right? Pullback, I mean that is how intersections were defined of sub-objects. So P is, so we can also say that P is isomorphic to image of alpha intersection, or you can say A, doesn't really matter, as A, alpha will induce an isomorphism from A to image of alpha. So image of alpha intersection kernel of beta. This is our P as well, right? So what we have is image of alpha intersection kernel of beta is actually 0, right? We have this. And what do we know about alpha? Okay, did I make a mistake here? I mean, am I overdoing things here? We assumed it and we have it. Something is wrong. Is a mono. We are given that beta alpha is a mono. We want to show that alpha is a mono. Okay, okay, yeah. Now I get my. I mean, yeah. I want to show that beta is a mono, right? I want to show kernel of beta is 0. What I'm saying is that's apparent, right? Because alpha is essential. We have assumed alpha is an essential mono. So image of alpha intersection kernel of beta, if is 0, then that implies kernel of beta is 0, right? Okay, now I get the point. I mean, yeah, sorry for the confusion. Yeah, this is no, it's okay. We are on the right track. I just got confused midway. Yeah. Okay. So what do we know? Beta composed alpha is a mono. So from that we have this information, and we know that P can also be written like this. So kernel of beta composed alpha is this, and since kernel of beta composed alpha is 0, so this is 0. Yeah, we are okay. Okay, so let's write it nicely. This is exactly kernel of beta composed alpha, which is equal to 0, isomorphic to 0, etc. This we have. Yeah, we were on the right track. Now we use the fact that since alpha is an essential mono, so beta, I mean kernel of beta has to be 0. So kernel of beta has to be 0, which implies that beta is a monomorphism. Done. So one side is done. We assume that beta composed alpha is a mono, and then we have shown that beta is a mono, and the essential thing, or the main thing that was used here is the fact that pullback squares are closed under gluing. That is what was exactly used. So this is like a tip for everyone who is trying to do categorical algebra, is to obtain intuition, to obtain the kind of argument to look for the right argument. What one should do is always assume that they are working with modules. We already know by courtesy of the Freud-Michel embedding theorem that this doesn't make much of a difference. There are some issues, but really doesn't make much of a difference. And what you do is you first of all write down your argument in terms of elements, because you are thinking about modules, and since you want to make an abstraction of it in more general category theoretic terms or in arrow theoretic terms, you try to phrase the entire argument in terms of arrows, so that this makes sense in an abstract abelian category as well, and then you write it properly. Interesting thing is, because abelian categories are so, because the category of abelian groups is so nice, so we already know what pullbacks exactly look like, what co-equalizers, equalizers, etc. look like, and trying to get from there to abstract categories is not very hard. Once you have understood your argument for modules or abelian groups, it's not very hard to phrase it in arrow theoretic terms, provided it is phraseable, of course. I mean, provided you are actually doing some category theory stuff. Okay, so one side of this is proven. Let's try to show the other side. So now what we do is we assume that our alpha has this property that whenever beta is any arrow from B to C, then the following statement holds that beta alpha is a mono implies beta is a mono. So let's write it properly so that we don't get confused, or I don't get confused. So conversely, assume that alpha from A to B has the property that for every beta from B to C, whenever beta compose alpha is a mono, then alpha is a mono. So then is probably not a right thing to say. Implies beta compose alpha is a mono implies beta alpha is a mono. I'm sorry, implies beta is a mono. Did I change the? Yeah, beta is a mono. So yeah, so we assume that alpha from A to B has this property that for every beta from B to C, beta compose alpha is a mono implies beta is a mono. What we want to show is that alpha is a essential monomorphism, and note that we were already given from the beginning that we start with a monomorphism alpha. So alpha is already given to be a monomorphism. This is not part of what we want to prove. This is given to us. This is a hypothesis. So what was I saying? Conversely, assume that the monomorphism alpha from A to B has this property. We want to show that alpha is an essential monomorphism. Oops. We want to show that alpha is an essential monomorphism. So how do you show this? How do you show this? Yeah, we have to go by that definition. That, so in other words, so we want to show that image of alpha is an essential subobject of what? Of B. So take okay, so yeah, so let B prime to B be a subobject of B such that image of alpha intersection B prime is 0. Okay. What we want to show is we claim that B prime is itself 0. That is what we need to show here. So how do you show this? So you can form this pullback square again. At least let's see if it's useful to us, but let's write it down. This is 0. B prime to B, image of alpha to B, this is given, this pullback square is given to be 0. What do you think? Can we conclude that B prime is also 0? So we have to, so let's just yeah, I mean since alpha is a mono, we'll not make a fuss out of it and let's call it A. So A to B we have alpha, which is already given to be a mono. Let's image of alpha, I mean let's just call it A intersection B prime equal to 0 to avoid any complications. Because alpha is a mono, this image of alpha is isomorphic to A. Okay. Yeah. So we have this data. We want to show that B prime is 0. We are given that alpha intersection B prime is 0. A is non-zero. I mean, we don't really know about that. I mean, it should be, but that won't matter much here. I mean, it depends on, I mean, if A were 0, then of course B would have to be simple. Oh no, B would have to be 0 as well. Because if provided alpha were an essential mono. Yeah. Yeah. Yes. So try to think about, yeah. Yeah. Okay. So the point is that what we want to show, we want to show that B prime is 0 as a sub-object of B, right? And what exactly do we have given to us? Something which we want to use is the fact that whenever alpha is post-composed with some beta, then if something happens, then something happens. That is, if beta compose alpha is a mono, then beta is a mono. So first of all, we need to find a relevant beta here which we can use. This is our first hint. So what relevant beta do you think can we use here? Something which comes after alpha. So let's have a diagram for this. I mean, I wouldn't really appreciate. Yeah. Kernel of what? No, but that would come before, right? I want something after. Co-kernel of what? Yeah, the question is we want some beta after B, right? Some beta after B which works. So let's have a picture for this. Let's, This is not really the way we should be thinking about this, but okay, no issues. So this is our B, this is our alpha. So what are we given about A and B prime? A and B prime intersect at 0, right? So let's write it this way. In a sense, so this is also sometimes called sometimes people say that co-products are disjoint to mean this, very roughly speaking. That's not exactly the correct meaning of the word, but yeah, in a sense, A and B prime are disjoint. Now think about this very properly. So suppose we wanted to take co-kernel of alpha, co-ker alpha, let's say. Then this composition would itself be 0, right? And it doesn't really make sense to, of course we want to use the fact that we want to use some beta such that beta compose alpha is a mono. So this composition is 0, so it doesn't really make sense to even expect it to be a mono, right? So that won't work. What we really want here, we want some kind of co-kernel here only, co-kernel of something, but in such a way that this composition is actually a monomorphism. And this is our hint, really. So what is this saying? This is saying that A intersection B prime is the 0 object, right? They don't really intersect, right? So that means that the kernel of alpha, if you look at the kernel of alpha, what was I going to say? Yeah. So I mean to say is, we can't take co-kernel of alpha, we should take co-kernel of something else. So that once, okay, so first of all, you guess I'll come with the intuition behind this. What do you think what co-kernel should we take here? Yeah, from B prime to B, we can take this co-kernel. Take co-kernel of B prime to B. So, what is this co-kernel written as? B prime is a sub-object of B. What is the co-kernel commonly written as? Yes, quotient of B by B prime. Right? So, we don't need to write on these names. Yeah. So B prime, B over B prime. Right? This is the co-kernel. Oops. This is the co-kernel of this map. Yeah. Now think about this very clearly. When would this epimorphism composed with alpha be, let's say, a monomorphism? When would this composition be a monomorphism? We want this composition to be a monomorphism. This would be a monomorphism provided it's the kernel of this composition is 0, right? And what does that mean? Alpha is already given to be a mono. What does that mean? That means that whatever, we don't really know, we know, but whatever is in the kernel of the epimorphism, the image of alpha cannot intersect it non-trivially, right? Because if it intersects it non-trivially, think of it in terms of modules again. If it intersects it non-trivially, there would be something which would go to 0 and would give you a non-trivial kernel of the composition, right? And that is exactly what is given to us. So we already have A intersection B prime is 0. So A, B prime. So check that. Okay, let's have a name for this. Yeah. Sorry? Provided of course we show that this actually happens. Q compose alpha is a monomorphism. And to check that is easy. You can figure an argument out. So how do you obtain this? How do you show that something is a monomorphism? Just show that it is its kernel is 0, or equivalently it's whenever we compose it with something, if the composition is 0, then the thing with the arrow with which we are composing it with is 0. So take some so this is just a rough to give some idea. Z to A takes a map. Assume that Q composed alpha. So if Q composed alpha composed this map H, let's say, is 0, what would we want really is this map H to be 0, right? Which means that what we would really want is H should factor through the 0 map. I mean, or the 0 object. It should factor over the 0 object. So, how do we show that there is a map from Z to 0? I mean, we know that there is, how do you show that H actually factors through this 0? To show that, we can use the fact that we haven't used it really. That just served as our intuition, but we want to use this fact that this intersection is 0. So we need to use the universal property of pullbacks. The point is that if Z to A composed with Q compose alpha compose Z, if this is 0, we can actually have a map from Z to B prime as well. And this is maybe an exercise for all the readers. Exercise, check using the universal property. The universal property of, one second, I'm sorry. Check using the universal property of pullbacks. Yeah, you wanted to say something. Did you have some comments? That there exists, that H factors over 0. Yeah, did you have some comment? Okay, so that would actually prove that Q compose alpha is a monomorphism, because what you would have is this composition and this composition are equal. This composition and this composition are equal. So what you would have is a unique map from this to this, which is exactly the 0 map, which would such that making the obvious two triangles commute. In particular, this composed with this would be equal to this, which would say that H is 0, right? So that would prove that Q compose alpha is a mono. So alpha is, sorry, okay, yeah, so alpha is a monomorphism by a, so Q is a monomorphism. Yeah, so Q is a monomorphism. What does that mean? So Q is a co-kernel and it's a monomorphism. What does that mean? And abelian categories are, yes, so since abelian categories are balanced, so by a balanced category we quickly recall that a balanced category is exactly a category in which a morphism which is both a monomorphism as well as an epimorphism is an isomorphism. So since abelian categories are balanced, hence Q is an isomorphism. It was already a monomorphism, I mean epimorphism. Yeah. Okay. Yeah, now what does this mean that this co-kernel map is an isomorphism? What does this mean? P prime should be, and why is that? Yes. So in other words, since it's a monomorphism, its kernel should be 0. And why is its kernel 0? Its kernel is 0 because B prime is the, I mean, why is B prime 0? B prime is exactly the kernel of this. So B prime equal to kernel, because Q is a monomorphism, B prime equal to kernel of Q is equal to 0. Okay, and that finishes the proof. So alpha is an essential mono. Any questions so far? Okay, we'll, I mean, the main problem that we want to stress today is problem 1. So we'll quickly wrap it up with problem 3, just may give some hints. So this is very interesting. One of the, another interesting property of abelian categories is, so as we know that for arbitrary categories, pullbacks of monomorphisms are always monomorphisms, but pullbacks of epimorphisms need not be epimorphisms. Can you think of an example, by the way? I mean, this is to all the viewers, where pullback of an epimorphism is not an epimorphism. Anyways, interesting property of abelian categories is that epimorphisms, when pulled back in an abelian category, are again epimorphisms. In other words, so what we mean here is this: if you take A to be an epimorphism, if you take C to be some arrow, then if you form this pullback square, then this, so let's call it F, let's call it G, let's call it F prime, let's call it G prime. So F prime from P to C is an AP. If F is an AP. Okay. So this is an interesting property of abelian categories. Yeah. So how do you show this? This is slightly, I mean, it's supposed to be a bit involved. Any ideas on how we can do this? So since we don't have a lot of time, I'll just give a hint on this. I want you guys to try. I'll just give the hint right now. We'll discuss. If there are any questions, people can email me or join the class at least once and ask. So show that. So 0 to E to A cross C to B to 0. Is this correct? Yeah. A cross C to B. What map do we have? This is a standard technique actually. Is an exact sequence. Just a minute. So P to A cross C we already have a map, which is F prime comma G prime. The map induced by the pair F prime comma G prime. And what map do you have from A cross C to B? Yeah, we do have a map from A cross C to B. Yeah, we do have a map from A cross C to B. What map is that? That map is just yeah. Okay. Yeah. Yeah. But F G are not composable, right? Do you mean F prime G? No, we don't. No, we don't need a pair of maps here, right? Because A cross we want to use the universal property of. We can't use the universal property of products here, right? We can use something else. What is that? We can use another universal property. What is that? To obtain a map from A cross C to B, we can use another universal property. What is that? What do you think? We can't use universal property of products, right? Because products are limits, right? So they are characterized by maps going into them. Yes, so we can use the universal property of coproducts, but that also we won't be using. The point here is this. It's a very simple point. So suppose you have a pullback square like this: P to C, A to B, C to B, G, A to B, F. Let's say this is G prime. Let's say this is F prime. Suppose you have a pullback square like this. The point is we know again that pullbacks and terminal objects suffice to give us all finite limits in our category, right? So we can write P and also equalizers and finite products, etc. So what I am trying to say is I can write pullbacks in terms of equalizers and products, right? So P can be written as an equalizer of two maps or can be written as a kernel of a certain map. So what map do you think it should be? So this is the reason actually. So P can actually be written as the equalizer of a pair of maps or maybe the kernel of a single map. We want a single map from A cross C to B. We can instead take a pair of maps from A cross C to B. Right? This is always true in any category. Take GF prime, take FG prime. The equalizer of this to will exactly be P. So what map are we asking for from A cross C to B? We are asking for kernel of, we are asking for Fg prime, let's say, minus Gf prime. So saying that this P can be written as an equalizer of this two is exactly saying that this sequence is exact. That's the idea. That is the idea. This part of the sequence is exact. That is the idea. Okay. And since F is assumed to be an AP, this sequence you can verify actually extends to this side, in the sense that this arrow will also be an AP. The map from A cross C to B will also be an AP. Okay. So this is our, I won't say much more because we don't have time. This is the hint that I will be giving, and I want the viewers to solve this. So what should I write? Equalizer. So check that. Pullbacks. We already know this. At least indirectly we know this, that pullbacks can be written as equalizers, using equalizers. Yes. Well, this is, so there is something called Doolittle squares in an abelian category. What are Doolittle squares? They are exactly squares which are both pullbacks as well as push-outs. And the interesting thing is that I might be a bit wrong in this, but it probably holds that if F is an epimorphism, then this pullback square will also be a push-out in addition. I might be a bit wrong. Okay, so the general way to show this thing, that pullbacks of APs is AP in an abelian category, is to use the following approach, that if F is an epimorphism, then you can also view this pullback square as this push out square. Okay. Did you understand what I'm saying? This is this. So now you think of this diagram and form this push out. The push out will exactly be B together with F and G as the structure arrows. Okay. So this actually becomes something called a pullation square or a Doolittle square, something which is both a pullback or as well as a push out. And apparently those are pretty important things. I don't exactly remember where I used them, but I'm pretty sure those things are pretty important. Was it satisfactory up to some extent? Okay, but still, this is really a powerful thing. You almost never expect epimorphisms to be stable under pullbacks, and this happens for an abelian category. This is really powerful as a statement. What was I going to say? Yeah, and binary products. Okay. Yeah, I'll just stop here, and should I say something more about this? No. Yeah, I think this is all. Epimorphisms are stable under pullbacks in the abelian category. Do we need to say something more? Now verify. I mean, use the fact that you have this exact sequence to verify that f prime is an epimorphism. If f is okay, we already assumed that f is. So let f be an ep. We used that f is an epi here to show that, to show that you actually, this sequence can be augmented with a 0 on the right. Okay, yeah, let's quickly get to problem 1, which is perhaps very important, and I really like this problem because this was the first problem that my advisor gave me when I went to him to join him. So yeah, what does it say actually? It's really powerful. It says that suppose C is a Grothendieck category. So we know what a Grothendieck category is right now. Let Ci be a family of objects in C. What we want to show is that this coproduct Ci is a sub-object of the product. So before going to abstract stuff, think about modules. Just recall how exactly was direct sum and product related. So what was product? Product in the category of abelian groups, let's say, is just product, the Cartesian product together with the component wise multiplication or addition. And what is the direct sum? Direct sum is a particular subgroup of your product consisting of those families of elements, one from each member, each factor of the product, such that all but finitely many are 0, right? So direct sum, which is a coproduct in the category of abelian groups, is a subgroup of the product, and we want to show something similar here. Okay, the result here is not that important, but the idea that I want to convey is really important. The trick, there's a trick in this, and that is what I want to convey, and that is what actually is related to our AB1, AB3, AB4, AB5. So when I say that, okay, so we'll come to this. Let's quickly give a small argument about this. Yeah, so how do you show that coproduct of CIs is a subobject of product of CIs? So first of all, what do we need to come up with is a map from coproduct of CIs to product of CIs, right? So what map should we take? Is there a canonical map from coproduct of CIs to product? Then we can attempt to show that that map is a mono, and since we want to show it's a mono, so the 0 map is already out of the picture. So we want a canonical map. I don't really like using the term canonical. We want a natural map, let's say, or still is not right. We want a map, let's say. This is what we want a priori. How do we obtain a map from the coproduct of CIs to product of CIs? To the coproduct, right? We have inclusions from CIs to the coproduct, yes, and right. Okay, so let's see. So we have from every Cj to the coproduct of I in I, Ci, we have our canonical co-projections, let's say. We are in an abelian category, we know that this will be a monomorphism. It's not true in general, of course. right? I mean, when you take an arbitrary coproduct in an arbitrary category or an arbitrary product in an arbitrary category, the projection maps need not be epimorphisms, right? Yeah. So we take Cj to the coproduct of Ci's, the inclusion. Let's say I, okay, let's say mu j, and we also have from product of Ci's I in I to each Ci, Cj, we have pi j. Yeah. How do we get our map? No, but no, but that would give you a map from product to coproduct, right? I mean, that would not really give you one map. That would give you a many maps from product to coproduct. Yes, and then we can use the universal property of coproducts. You are close. Yes. So it's just the what is that Kronecker delta, right? So for, let's say j comma, let's have one more variable which is different from I, k. Jk in I, we take the map to, what is this, Cj to Ck delta Jk, the Kronecker delta. Now keep for fixed j I, this induces a map, a morphism Cj to product of Ck's, or let's say Ci's, I in I, Pj, let's say. P is P, Fj, let's say. For each j, for each fixed j in j, we have this. So for, hence we have a map. We know how we are getting these arrows. Hence we have a morphism using the universal property now of the coproduct. Earlier we used the universal property of the product. We have a morphism from coproduct of Cj's, j in j, or let's say Ci, I in I to product of Ci's, I in I. What is the interesting thing? I mean, what exactly do we need to also write? This map should be the unique map satisfying this commutative square, right? I mean, filling this commutative square. We have a morphism, let's say F. So the following diagram commutes. For j in I, comma k in I. What is our diagram? It's just the obvious one. I in I, F, the single map making every small thing commute. I in I. We have Ci, Cj to this. This is our mu j. Did we write this or erase this? Yeah. And from this to this we have pi j, pi k, Ck. This is delta Ik. This commutes. F makes this commute. Okay, so interesting thing, we already have a morphism F from the coproduct to the product. Now how do we show that this morphism F is actually a monomorphism? That would actually finish the job, right? So just shoot random ideas how do you think it should be doable? Some keep in mind that we have it. Yeah. Okay, we can try with the kernel. Yes, we can try the kernel. And in fact, trying with the kernel will also work. But okay, so let's rephrase the question. How do we exactly use the fact that we have a Grothendieck category? How do we use? Okay, but do we have that actually, or do we know that? In the definition of a Grothendieck category, what we have is it's a co-complete abelian category which satisfies AB5 and has a generator. That's all, right? So we don't know if it is AB3 or not. So we need to somehow use the fact that direct limits are exact. So tell me, so when we say direct limits are exact, saying, I mean, what is a minimal thing that needs to be said, which is equivalent to saying that direct limits are exact? Is the question understandable? I mean, what guarantees? I mean, what direct limits? We okay. So direct limits are exact means direct limits are left exact as well as right exact. Is something automatic in this? Yeah. The question is, we know that in a Grothendieck category we want direct limits to be exact. That is what AB5 says. So when we say direct limits are exact, this means that direct limits are left exact as well as right exact. So my question is, which part of this is automatic? I mean, which part of this is true? We don't need to assume. What do you think? Which part of this is already true to us? I mean, already we know this, or at least we can guess that this should be true. So direct limit is a co-limit, right? So you can actually verify if you write down the sequences. Let's say you write 3 sequences indexed by the directed set I. You can actually verify that direct limits will be automatically right exact. So in the sense that if you take AI to BI to CI to 0, and if you take the direct limit will also be exact. I mean, the direct limit will all, I mean, this sequence limit AI to limit BI to limit CI to 0 will also be exact. That part is automatic to us. What we, I mean, what needs to be assumed to say that direct limits is exact is direct limits are right, I mean, left exact. That is, in other words, it means that direct limits preserve kernels, or equivalently, since kernels and monomorphisms are old friends, we can just say that direct limits preserve monomorphism. So the point is, to simplify what AB5 says is, so AB5 says, AB5 can be rephrased as if I is a directed set, and for each I there exists a monomorphism if I from AI to BI. Okay, we have already passed 8. If I from AI to BI together with, for each I less than I prime, less than equal to I prime in I, an arrow morphism AI to BI AI prime to BI prime, or morphisms, sorry, making this commute, making the diagram commute, then what? Then direct limit AI finite to direct limit, I mean co-limit, I is a directed set, BI, this co-limit Fi, this is a monomorphism. This is actually enough. This is exactly what AB5 says. This is exactly equivalent to what AB5 says. If you have a directed family of monomorphisms, then taking the direct limit, I mean monomorphisms are stable under taking direct limits. Okay, so we are at least one step closer to what we want. Yeah. Yeah, so we are at least one step closer to showing that F is a monomorphism. We have a better condition at hand. So we want to show that F is a monomorphism. Okay. So now, what do we do? So here I is just a set, Ci is just a family of objects indexed by the set I. We don't actually have a directed family. But this is the trick that I am talking about. We want to use some trick that so as to bring direct limits into the picture. What exactly is it? What exactly can we do here? What do you think? And this is, I mean, okay, what exactly should we do here? Yeah, we want to bring direct limits into the picture. We just have coproducts. So my question is this: can coproducts be equivalently be written in terms of direct limits? Okay. Okay, you are very close. You are very close to the idea. So what exactly are we taking? Yeah, but the issue here is I is an arbitrary set, right? So we don't really know if it's denumerable. Of course, we can well order it and say an argument like this, but maybe something simpler which refines everything. You are very close actually. So C1 coproduct C2, C1 coproduct C2 to maybe C1 coproduct C3. That is what you wanted to say. So you are very close. What exactly are we taking here? Yeah, so what exactly are we doing? We want to bring a directed set into the picture. We want to sort of replace an arbitrary discrete, I mean a set by some directed set. What is the best way that one we can do? What is the best way to go about this? The best thing to do would be to look at finite subsets of I, right? Because finite subsets form a directed set. And that is the trick. So this is our trick that we use. So this is our trick that we use. So trick is replace so we want to replace the finite set. I mean sorry, we want to replace the arbitrary set I by a directed set. So I'll just mention the trick quickly. What we do is let f, let's say, be the family of finite sets, finite subsets of I. It's exactly something like prove that module is a directed limit of its finitely generated submodules. Prove that a set is a direct limit of its or a filtered co-limit of its finite subsets, etc. So let F be the collection of all finite subsets of I. F with inclusion is a directed set and hence a category. It's a filtered category. So we can talk about direct limits right now. And so what we actually want to show here is this. This is what we want to show finally. So verify, I won't say check that because this needs to be verified. Verify that the coproduct of CI's I in I should be isomorphic to, I mean there should be a natural isomorphism, I should say, canonical isomorphism, I should say. There exists a canonical isomorphism from the coproduct of CI's I in I to the product of CI's I in I. I'm sorry. Coproduct of CI's I in I to the, what is it I wanted to say? Yeah, to the limit. Yeah, to the direct limit of S in F, comma this. So S is a finite subset of the coproduct S, little s in capital S, CS. So there exists a canonical isomorphism, and not only so, the point is that such that coproduct CI I in I iso limit S in F, comma this coproduct S in S CS. We already have an arrow from this to the product, which we wanted to show is a monomorphism, and we also have an arrow from this to the product, such that this commutes, this triangle commutes, and verify that. Okay, so I mean, what is this dashed arrow that we are talking about here? So the problem has right now been reduced to working with finite subsets of I, right? So just take an arbitrary finite subset of I, show that if S is a finite subset of I, that is if S belongs to the family F, then the composite morphism is S CS to coproduct I in I CI to product I in I CI F is a monomorphism. See, the interesting thing is this, that now that we are reduced to dealing with finite coproducts, you can treat them as finite products as well. You can do a lot of things here, and and actually you can prove that this is a monomorphism. I mean, that would be easier to show. Okay, so you can show that this composition is a monomorphism, and then
Hello?
using AB5. I'm sorry, I'm talking 2 minutes.
ও আমার বললে না ওদের তো ফোন নেই এখানে দাও আমি একটু ফ্রেশ হয়ে তারপর দেখছি এদের ফোন আছে নাকি রুমে
Using AB5, this implies that this composition will be a monomorphism, and that is all that we wanted to show. I mean, this composition that we have here is exactly where I haven't made any mistakes. Yeah. Yeah, I mean, let's just cite this as from this is isomorphic to the co-product I9 CI. I mean, you can fill in the details. Product CI I9 F. This implies that this F is a monomorphism just by using the AB5 axiom directly. Okay. Yeah. Let's erase this. I mean, of course, there will be a canonical isomorphism making this commute, but I mean, yeah, okay. I mean, there's no harm in writing this. Provided it doesn't confuse. Yeah, okay, there's no harm. So basically, when I'm saying this composition, I'm actually using this composed with this. And we have already shown this is a monomorphism, hence this will be a monomorphism. Because you have an iso here. Okay. Yeah, that's all that I want. Yeah. So the final thing that I wanted to say is why is this trick so relevant in particular? Since we now know that coproducts can be written in terms of direct limits. So can you conclude what does this mean in as far as the axioms AB3, AB4 and AB5 are concerned? So for a Grothendieck category, we have just assumed that we have AB3, AB5 and a generator. We didn't assume AB4, and that was because now that we know that coproducts can be written as direct limits, so Yes. So co-products in particular are exact as well, because direct limits are exact, and co-products in a Grothendieck category can be written as direct limits. So they are also exact. So AB5 implies AB4, which is pretty strong. Okay, maybe I'll stop here for today. And are there any questions? Okay. See you next week, week 11 of the course, and goodbye.